Is hypothesis to theory, in which we're going to see how we tested the nebular hypothesis so that we could call it the nebular theory. Last day we looked at the development of nebular hypothesis and how it illustrates the scientific method, the approach that scientists today take to trying to understand nature. You will remember that all knowledge begins with a question, and in the case of nebular hypothesis, the question we started with was, how did the solar system form? The next step in a scientific approach to a problem is to collect evidence, to rely on empiricism and observe everything you can related to that question, in this case, the question of how the solar system formed. So we looked at empirical facts about the solar system, things like its size, the fact that it's basically flat, that almost everything moves in the same direction, that there are two types of planets, the small rocky planets close to the sun, the large gas giants farther out, that there are small little chunks of rock called asteroids, mostly between Mars and Jupiter in the asteroid belt, and that at the outer reaches of the solar system, we have the icy trans-Neptunian objects. We then added to this data general knowledge that we have about both space and matter. So we talked about the type of matter that exists in space, the interstellar medium of gas, mostly gas, 99% gas, 1% dust, how this matter in some places is pulled together into clouds of gas and dust called nebulae, pulled together by gravity. And then we also brought in some details from a basic theory of matter that we have, the kinetic molecular theory. We used deductive reasoning then from all of this data to come up with a hypothesis, a possible answer to our question of how the solar system formed. What we were doing basically was, in developing nebular hypothesis, coming up with an antecedent, actually not a single antecedent, but a set of antecedents that, when they're plugged into a deductive argument, logically give us these observational facts as consequence that follow from it. So the details of nebular hypothesis were these: that we believe the solar system started as a nebula, we call it the solar nebula, cloud of gas and dust about 5 billion years ago. Gravity began pulling this matter together inwards. And in the process, the matter heated up according to the gas laws of chemistry, and because it was slowly rotating, it would flatten out according to the law of conservation of angular momentum and centrifugal force. It would flatten into what we call a protoplanetary disk. The center of it heated up the most and became the proto-sun. And once it reached about 10 million Kelvin, it got hot enough for nuclear fusion to begin, and the sun was born. In the meantime, out in the protoplanetary disk, the dust was accreting, and in some cases far out from the sun where it was cold, collecting gas to form the planets, the gas giants. And then once the sun ignited, the solar wind, these high energy particles streaming out from the sun, blew the remaining nebular material away, and we were left with the solar system. So that took us up to our nebular hypothesis, an idea that explains all the observational data that we'd already collected. But remember, in science, we do not accept a hypothesis simply because it explains things. We actually need to test that hypothesis by using deductive reasoning to make observable predictions, and also then to use empiricism to see if the predictions that we made actually come true. So that's what we're going to look at in today's lesson.